right, we want to look at Chapter 7. This is the central limit theorem. And Section 7.1 is the central limit theorem for sample means or averages. Let's say that you had an unfair die. So you roll it 4 times and you get a 1, a 1, a 3, and a 6. I mean, that's not likely, right? You should not get the same number twice if they equally have a 1 in 6 chance of coming up. And so then you do a second sample where you roll it 4 more times, and again you get 2 3s. And you do a third sample where you roll it 4 times, and you get 2 1s and 2 6s. If we went through and we made a histogram of that information is nowhere near normal. I've got a whole lot more 1s than I do anything else. I didn't get any 2s. I didn't get any 5s. However, if I went back and I found the mean of each of these samples, so 1 plus 1 plus 3 plus 6, and I divided that by 4, I'd get 2.75. And then 3 plus 4 plus 3 plus 1, divide that by 4, I get 2.75. And then 1 plus 1 plus 6 plus 6, divide that by 4, I get 3.5. If I kept doing that, those samples, when I graph them, those sample means would appear to make a normal distribution. And so that is the idea that leads us to the central limit theorem for sample means or averages. So suppose X is a random variable with a distribution you may know, you may not know. It can be any kind of distribution. So it could be uniform, or it could be normal, or it could be any of those that we have studied. And so, of course, our mean, there's our same notation that we've been using for our population mean, our population standard deviation. If you draw random sample sizes of n, then as n increases, the random variable will consist of sample means and tend to be normally distributed. Okay, let's talk about that for just a second. So n, the sample size. If we go back to what we were doing just a moment ago, this was our sample size, right? We were rolling 4 times. So that would be our n value, not that we did this 3 different samples, but it's the number of things that are in our sample. So we want that number to get larger and larger. That variable n, that sample size, is the number of values that are averaged together, not the number of times the experiment is done. And if those sizes increase, then the random variable that is made up of those sample means will form a normal distribution. All right, so how could we express that? Okay, well, we could say, here's our sample mean, right? That's our notation for sample mean. Our sample mean is going to be an approximate normal distribution using these 2 values, and the first one's going to be the population mean, and the second one is going to be the population standard deviation divided by the square root of the sample size. Now, we'll come back to that in just a moment, but notice that that is different moving forward for this specific theorem. Okay, so the central limit theorem for sample means says that if you keep drawing those larger and larger samples, so maybe you roll the die 1 time, and then you roll it 10 times, and then you roll it 20 times, or you roll 20 different die, that sample size is getting larger and larger for each one of the samples that you're taking. So then if you'll go back and you'll calculate the means of each of those samples, they will form a normal distribution, and we also call that a sampling distribution. Now, that normal distribution will have the same mean as the original, and the variance, as we said, is going to equal the original variance divided by n, the sample size. Because again, if you take your standard deviation and divide it by the square root of n, remember, if you square the standard deviation, you get your variance. So to put it more formally, if you draw random samples of size n, the distribution of that random sample variable that's consisting of those sample means is called the sampling distribution of the mean. The sampling distribution of the mean approaches a normal distribution when the sample size increases. All right, and so here's that same formula that we saw a second ago. Our standard deviation is going to be divided by the square root of the sample size, and that standard deviation is also called the standard error of the mean. And if you wanted to find your z-score, that would still be your data value minus your mean divided by your standard deviation. Now, that was a lot of information and a lot of terminology. It makes a lot more sense if we actually put it into a problem. So let's look at one. Okay, it says an unknown distribution has a mean of 90, so there's our mean right there, a standard deviation of 15, and a sample size of 25, so there's our n value, and they're drawn randomly from the population. So they ask us to find the probability that the sample mean is between 85 and 92. All right, so the first thing that I need to do is remember that my standard deviation has to be divided by the square root of n for this, right? So the standard deviation they gave me was 15, and I'm going to divide that by the square root of n. The n they gave me was 25. So square root of 25 would be 5, 15 divided by 5 was 3, and 3 would also be called the standard error of the mean if they asked us to identify that. All right, so if we're going to let x be one value from the original unknown population, the probability that we want to find for the sample mean is between 85 and 92. Now, we said the sample mean would be normally distributed. So we're going to do a normal distribution for this. And for your normal distribution, remember that you use the mean and the standard deviation. All right. So now that we've got our normal distribution set up to find the probability between 85 and 92, we do that on our graphing calculator. So grab your graphing calculator if you would, please. All right, and remember that the way that you find your normal CDF is you go to distribution, so second distribution, and then select normal CDF. Now, for your normal CDF, if you have your wizard on, it's going to prompt you for your lower value of 85, your upper value of 92, your mean of 90, and your standard deviation of 3, or if you don't want your wizard on and you would rather just type it in directly on your own, you can do that as well. So you can see that the probability that that sample mean is between 85 and 92 would be this 0.6997. All right, then it says find the value that is 2 standard deviations above the expected value 90 of the sample mean. Okay, well, if the mean is 90 and the standard deviation is 3 and we want to be 2 standard deviations above that, you could use common sense and say 90 plus 3 plus 3. Or if you're more of a formula person, you could say take the mean and add the standard deviation 2 times. So again, 90 plus 2 times 3. Either way, that's going to give us 96. All right, in a recent study on the Flurry blog, the mean age of tablet users is 34. All right, so there's our mean. Suppose the standard deviation is 15, so there's our standard deviation, and the sample size is 100, so that's going to be our n value. So it says, what are the mean and standard deviation for the sample mean ages of the tablet users? Okay, so our mean is 34. But for our standard deviation, remember we have to divide it by the square root of the sample size. So the standard deviation was 15, and it gets divided by the square root of sample size, which was 100. So that would be 1.5. All right, then number 2, what is that distribution going to look like? Well, the central limit theorem told us that that distribution will be approaching a normal distribution. It will be approximately normal. So we want to use a normal distribution for C to find the probability that the sample mean age is more than 30. All right, so if I want to find the probability that it's more than 30, then remember I'm going to use a normal CDF, and I'm going to give my lowest value, my highest value. Now we can't say infinity, so we say 1e to the 99, and then our mean that we had from here, and our standard deviation that we had from here. All right, so if we throw that into the normal CDF in the distribution menu on our calculator, so again, I just put in my lower, my upper, my mean, and my standard deviation, then it will shoot out that probability for me. All right, then for D, it said find the 95th percentile. Now this is when we're going the opposite way, right? When we're doing the inverse of that, when we do inverse norm. So for the 95th percentile, I'm going to write that as 0.95. And again, I'm going to use my same mean and my same standard deviation. So again, go to your distribution menu and go down to inverse norm. And then we're going to put in our percentile as our area, our mean, and our standard deviation. Now, this area is always to the left, remember? So we always select left. If your calculator doesn't have that as an option, you don't have to worry about it. And so that gives us our 36.46, or that 36.5 that we're seeing there for our solution. All right. So let's try another one of these. If you want to work with someone around you, you are welcome to do so. So if you want to slide into a group and work with a couple of other people, you can. But for this one, it says the mean number of minutes of app engagement by a tablet user is 8.2 minutes. Suppose the standard deviation is 1 minute, and take a sample of 60. All right, so the first thing we want to figure out is what's our mean? What's our standard deviation, and what's our sample size, right? Okay, so what's your mean? It's 8.2. Your sample size is 60. It's n. So our standard deviation then is going to be 1 divided by the square root of the sample size. So 1 divided by the square root of 60. All right, so now we've got our mean and our standard deviation. All right, then B, it says find the 90th percentile for the sample mean. All right, so how do we find the 90th percentile again? Is that norm or inverse norm? All right, so that one's inverse norm, right? And 90th percentile, we'll write that as a decimal, as 0.90. That's our area. And then again, we use that same mean and that same standard deviation. So when we put that in our calculator, in our distribution menu, and we choose the inverse norm, it lets us enter our area, our mean, our standard deviation, and again, it's always left, and that is generating that 8.37 solution that we're getting there. Now, it says interpret that value in a complete sentence. Like, what is that we just found? Well, that shows that 90% of the average app engagement time for these tablet users is going to be less than 8.37 minutes. So 90%, everything to the left, so everything but the top 10% are going to be in less than 8.37 minutes. All right, then for C, find the probability that the sample mean is between 8 minutes and 8.5 minutes. All right, so if we're finding probability, not percentile, but if we're finding probability, do we do inverse norm for that, or do we do norm CDF for that? So that one we do norm CDF, right? All right, so for the normal CDF, if we're finding the probability between this is our low value and this is our high value, remember we do the lowest value, the highest value, the mean, the standard deviation. And so again, what that looks like on our calculator is we go to distribution and choose normal CDF, and then it will prompt us for each of those values, the lower, the upper, the mean, and the standard deviation. Or you can type it in directly without your wizard if you want to. And in either case, we'll end up with that value that we were looking for, the 0.9293. All right, section 7.2 is the central limit theorem for sums. All right, just a second ago, we were looking at the central limit theorem for averages, for means, right? This is the central limit theorem for their sums. So suppose that x is a random variable with a distribution that may be known or unknown. So again, it might be normal, it might be uniform, it might be something else. And suppose that we still have our population mean and we still have our population standard deviation. If you draw random samples of size n, then just like before, as n increases, the random variable, the sum of those x values, consisting of the sums, would also tend to be normally distributed. So instead of finding the average of your samples, you would find the sum of your samples. So if that is the case, this mean and standard deviation are going to be different, right? Because if I'm trying to find the mean of the sums, then I'm going to take the number of them that I have times the mean. And if I'm trying to find the standard deviation of the sums, I'm going to take the square root of the sample size, the number that I have, times the standard deviation. When I do that, it tells me that the sum of those values should be normally distributed with this as my mean and this is my standard deviation. And again, we're just talking about the sum of x as being a sum, and of course we could express our z-score in that way as well. So the central limit theorem for sums says that if you keep drawing larger and larger sample sizes and you add up the sum of all of the things in your sample, then those sums, when you graph them out, they would form their own normal distribution or a sampling distribution that would appear normal as that sample size increases. Okay, so let's look at one of these. An unknown distribution has a mean of 90 and a standard deviation of 15. A sample of size 80 is drawn randomly from the population. So first off, find the probability that the sum of the 80 values, or the total of the 80 values, is more than 7,500. Okay, well, I need to figure out what my mean and my standard deviation are going to be before I start plugging them into formulas. Because remember, I have to calculate them. The mean of the sum is going to be the sample size times the mean. And the standard deviation of the sum is going to be the square root of the sample size times the standard deviation. All right, so let's come back up here. The unknown distribution has a mean of 90. So we're going to put 90 right here for our mean. And it has a standard deviation of 15. So we're going to put 15 right here for our standard deviation. And then a sample size of 80. So we're going to put 80 in for this n and 80 under the radical n for this n. All right. So our n is 80. Our mean is 90. We multiply those and get 7,200 for our mean of the sum. And then our standard deviation was the square root of n, and n was 80, times the standard deviation, which was 15. So the standard deviation of our sum is going to be 134.16. Those are the values that I want to use for calculating the sum of x. All right, so when it says find the probability that the sum of the 80x values is more than 7,500, again, I know this is a normal distribution. So I'm going to do a normal CDF. I'm going to give it my lower value. So it says it's more than 7,500. So my lowest value would be 7,500. And I'd be going to infinity. So my upper value would be 1e to the 99. Our mean was 7,200. And our standard deviation was 134.16. So I throw that into my calculator, and that's where the book is getting this value of 0.0127. All right, look at B. B says find the sum that is 1.5 standard deviations above the mean of the sums. Okay, well, first off, what's the mean of the sums? Well, here it is right here. The mean of the sums is 7,200. And I want to find 1.5 standard deviations above that. So I'm going to take the 7,200 and I'm going to add this standard deviation 1.5 times. So I'm going to take the 7,200 and I'm going to add my standard deviation times 1.5, and that gives me my answer for B. All right, then section 7.3 talks about how to use the central limit theorem. The central limit theorem goes hand in hand with the law of large numbers. Now, we've talked about the law of large numbers before. It just says that if you take samples of larger and larger sizes from any population, then the mean of the sample becomes a better and better approximation of the mean of the population. From the central limit theorem, we know that as our sample size gets larger and larger, that the sample means follow a normal distribution. So the larger that sample size gets, the smaller the standard deviation is going to get. So that means that our sample mean is going to be close to the population mean. And we could say that the population mean is the value that the sample mean approaches as the sample size n gets larger. And that is exactly what we've said before. That is what the central limit theorem illustrates for the law of large numbers. So you can see how these two pieces fit together. All right, let's look at another example. A study involving stress is conducted among the students on a college campus. The stress scores follow a uniform distribution, so they've told me that it's uniform this time, not normal. That's different. That's section 5.2. That's the one that has the A and the B values in it. So we'll talk about that in just a minute. With the lowest stress score equal to 1 and the highest equal to 5. And they sampled 75 students. So they asked 75 students, how stressed out are you? 1 being the lowest, 5 being the highest. All right. So they want us to find the probability of the mean stress score being less than 2 and the probability of the mean stress score being the 90th percentile. Then they want me to switch and find the total of the 75. That's the sum, right? And then the total, that's the sum. So the first two, we're using the mean. The second two, we're using the sum. And remember, we have different formulas for those. So problems A and B ask you to find a probability or a percentile for the mean. Problems C and D ask you to find a probability or percentile for the total or the sum. Okay, so let's look through this one piece at a time. Since they told us that this was a uniform distribution, in section 5.2, remember a uniform distribution has an A and a B value, where A is the lowest value and B is the highest value. So they told us that when they asked the students how stressed out they were, the lowest score they could give was a 1, and the highest score they could give was a 5. Now, in section 5.2, in the uniform distribution, these were the formulas that we had for mean and standard deviation. So mean was the A plus the B value divided by 2, and standard deviation was the square root of B minus A squared over 12. We had that on our last test. So let's plug those numbers in. If A is 1 and B is 5, that's going to give us 6 over 2, or 3 for our uniform mean. And if B is 5 and A is 1, then that's going to give us 4 squared, or 16 over 12. And then the square root of that would be 1.15 for our standard deviation. All right, so now we have the numbers that we need to compute our values. So for A, it says find the probability that the mean stress score for the 75 students is less than 2. Now, if it's less than 2, I'm going to do a normal CDF. Remember, when you want the percentile, you do the inverse norm. When you want a probability, you do the normal CDF. All right, but look at the numbers that we have here. All right, we have our lowest number, which is 1. We have our highest number, which is 2. We have our mean, which is 3, and this is not that standard deviation right there. Because remember that when it is a mean score, you always take the standard deviation and divide it by the square root of the sample size. That's the easiest thing to forget. So star that or highlight it. That's the one thing we really have to watch out for here. Okay, so I put that in my calculator. So again, the lowest score they could have asked, or they could have listed, was a 1. They want us to find the probability less than 2, so that's going to be our high. The mean was 3, And then the standard deviation was the standard deviation divided by the square root of n. And so that would give us 0. All right. Then the second one said find the 90th percentile for the mean stress score. So this is where we go the opposite way, right? We do inverse norm. So let's do that. Let's go to distribution and choose inverse norm. And our probability, or our percentile, written as a decimal, is 0.90. And then our mean, and again for our standard deviation, we do not use the 1.15. We have to take the 1.15 and divide it by the square root of n because it is a sample mean. All right, so we'll put those in the inverse norm in our calculator. So again, we'll go to distribution, select inverse norm, and we'll put in our area or probability or percentile as a decimal, our mean, and then that standard deviation divided by the square root of n. Always the area to the left, whether your calculator has that option or not. And then that will give us our 3.2. Okay, so A and B, they wanted the mean stress score, right? C and D, they want the sum. So we have to find a different formula for the sum, right? Remember that when you have the sum of the means, you use n times the mean. So for us, the sample size n was 75 and the mean was 3. So that'll give us 225. And then if I want the standard deviation, I do the square root of the sample size times the standard deviation. So the square root of the sample size times the standard deviation is going to give us 9.96. All right. So I want to be careful that when I'm doing the mean, that I use those formulas. When I'm doing the sum, I use these formulas. All right. So for C, it says find the probability that the total of the 75 stress scores is less than 200. Okay. So probability, we do normal CDF. So I'm going to choose normal CDF and I want it to be less than 200. All right. So my lowest value is going to be 75. Oh, hang on. I thought the lowest value they could report was 1. Yeah, it is. But if you ask 75 students what their stress level is and the lowest response they can give is 1, then what's your lowest sum? 75. Let me say that one more time. We're finding the sum of the 75 scores. If you asked 75 students what their stress level was and the lowest number they could give was a 1, the lowest value you could have would be the sum of 75 ones. It would be 75, right? Okay, so my lowest number is going to be 75. My highest number is going to be 200 because we're looking for the probability less than 200. My mean is going to be 225, and my standard deviation is going to be 9.96. All right, so putting that into our calculator, lower, upper, mean, standard deviation, you can see where we get that 0.006. And again, just a reminder there that the smallest total of 75 stress scores is 75 because the smallest single score is a 1. That's where we got that 75. All right, then for D, it said the 90th percentile for that total, for that sum. All right, so when we're doing percentiles, again, we do inverse norm, right? So let's do inverse norm for 0.90. And again, because it's the sum, we're using the 225 and the 9.96. So you can see when we put that into our calculator, here's our area, our mean, our standard deviation, always to the left, and that will give us that value that you see there, the 237.8.